I hope you like the quote. This is from a British science fiction author, Scottish science fiction author, Charles Stross. He's written a lot of sort of near-future science fiction. He stopped writing it now because whatever he wrote started coming true, and it freaked him out. It's a true story. But he sort of describes, as he says here, AGI is already here. We just work in them, operating or executing their algorithms and heuristics very, very slowly. The companies that we're working have these processes that we as humans participate in, like ants in an ant nest. So to start off with a really positive message, that's kind of what we are, right? We're people who do stuff. Well, we do knowledge work. Most of us here, we take a thing that's less valuable, like a user story or something, or maybe it's an idea that needs to be fleshed out and broken up into a set of epics, or business requirements document that needs to be turned into a set of solution options or architecture options. And then, we do the stuff and then we produce it. And it's slightly more valuable. And then over time, those things move through a series of steps, the artifacts, until they become something that's most valuable, which is either like maybe it's working software for what we do, that's making money or saving lives, or in the case of physical products, goods moving through a factory, going from raw materials until you can finally buy the car at the end. A series of steps, activities, processes where value is gradually added to a thing until at the end we have a more valuable thing. So what I'm going to be talking about today is that world, the world in which we work, how flow works in that world, how things flow through the systems that we participate in on our teams, and in our organizations. I'll give you some tips about how we can optimize some of this stuff, optimize the world of work, optimize the system that we participate in. I think I'll also, you'll be pleased to know, talk a little bit about agents. I'll call them agents, not agentic or something, because I'm old school. So there's some agent stuff at the end, some agentic stuff at the end, some AI, Gen AI stuff at the end, because I think we're at the verge of being able to use some of these tools from Gen AI and from previous iterations of AI to really do some interesting things in the world of work. So as I said, this is the talk. It's how flow works, and because my mind is full of stuff, it's called How Flow Works and Other Curiosities. So this is the culmination of a journey for me that started probably about 2017. When I was, spent a lot of time working with microservices, looking at software architecture, as a software architect, enterprise architect, whatever you want to call it. And I sort of became fascinated by the intersection of how the stuff we build, design, and then build and deploy, how that intersects with how the organizations in which we work. You've probably come across Conway's Law before. Conway's Law was written, I think, 1959 or 69, I get the decades wrong, a long time ago. And Mel Conway stated that the software that a team produces, the design of that software will mimic the design of the team that builds the software. Or the software that an organization builds mimics the design of the organization itself. It's to do with information theory. It's to do with how information flows between people on teams, how we communicate. And it seems like this law holds. So if you operate in a system where you've got a UI team and you've got a back-end team, a database team, you'll end up with a UI, some back-end, and a database. I'll give you another concrete example of this, and Netflix. I mentioned this, I think, maybe yesterday in my talk. The way Netflix organized is around Conway's Law. So they say, we'll have all of our UI teams, right? All the UI teams will be sitting at one end of the building, and they're the people building, the software for the clients. So for, for TVs and for mobile phones and for the web and so on. Next to them will be the platform API team, and they coordinate, I think it's by GraphQL these days, they mediate access to the services behind. Then you have the service teams, the microservice teams. So you've got UI, platform, microservice teams, and way over here, you've got the database admins, right? The Cassandra admins, the network admins, and so on. And this is designing an organization according to Conway's Law, right? So we're saying We don't need the people who are building UIs to talk to the Cassandra people. So they don't need to sit together. But it would be really good if the UI teams had really high bandwidth communication between them and the platform API team. So let's sit them close together so when they want to do stuff, they can say, hey, platform API people, I'd like to do a thing. Can you help? So that's Conway's Law. And that's why I sort of got into this thinking about flow and how flow works, how the system of work works. It's been quite a journey. I'll come to some of the things I've done a bit later. But I'd like to ask you this question first, because I'll be coming back to it at the end. If you were in charge of making or building Lego sets, if you wanted to make that experience better, what single change would you make? Now, I only found this out last night. I'm an adult friend of Lego, which is a self-confessed thing. I like building big Lego sets. And I think I only found out last night that Lego wasn't a thing in India. Is that right? But there was a different Mega Blocks or something was the equivalent. So you can, /s/Lego/Leg Mega Blocks, right? For this, but the same thing, right? Same deal. How would you make the experience of building big sets out of these little things better? If you don't know who I am, my name is James. I work for ThoughtWorks. We are a software consultancy, 2 offices in this city, many more in India, many more around the world. I wrote a thing some years ago which went on to become the definition of microservices, and more recently I've been writing about legacy displacement because someone has to, because we have not cracked it yet and no one else is really writing about it, so we thought we might as well do it. And hopefully this will turn into a book at some point. But the problem is with me, deadlines fly past, which none of that. So at some point it'll turn into a book. Okay, so I mentioned I'm going to talk about the system of work that we participate in. Who's come across the idea of a value stream? Put a hand up. I'm trying to keep you all awake here with some movement. Cool. Some people, most people haven't. That's really interesting, actually, and really good, because I can hopefully teach you some stuff today. So work flows as information through value streams, or why shared test environments should be nuked from orbit, because it's the only way to be sure. Quick alien gag or reference. So, I said this, work flows as information through value streams. There's a lot. This seems like a simple statement. There's a lot to unpack in this. So work, what do I mean by work? Well, as I said at the start, as knowledge workers, it's invisible stuff, right? It's the sort of ideas, it's the stuff that's written as user stories or epics, it's the code we write that's committed into a repository, it's the testing we do, those value-adding activities is what I mean, that we apply to the work, we apply to the things that's moving through these value streams. So this work flows through these value streams as information, as in what we do. And the information bit is crucial, because one of the big problems we've got as knowledge workers is we can't see a lot of the work, right? It's invisible to us because it sits in computers, right? Now, if you think you're in, say, a car manufacturing plant, right? And you've got a series of machines that build bits of the car. You've got an assembly line that's putting it all together. If you're at the assembly line and the manager sees a whole ton of widgets building up and building up and building up and building up, you'd immediately know there's a problem, right? You'd go, there's too many widgets here. We're holding too much inventory. This is cost on our books. We need to do something about it. Go faster, reduce the amount of inventory we hold. Physical stuff we can see. What we do, we can't see unless we make it visible, right? Unless we put it into Jira's backlogs or that kind of stuff. And this is a really pernicious thing because we don't tend to see or think about stuff sitting in our system of work as inventory in the same way that widgets in a manufacturing plant are inventory. Unfinished work sitting as cost on our books. That's unpacking that a little bit. What do I mean by value streams? So this is a very simple value stream from a previous client, which I've anonymized clearly. It's very simple. What you can see on here is a series of 3 activities. We've got development, we've got testing, and we've got deployment. Development on average takes 3 days. Testing on average takes 1.5 days, and deployment on average takes half a day, right? So in total, a user story enters here, has 3 days of development, 1.5 days of testing, and a half a day. So what's that? Well, 5 days of value-adding stuff, people working, adding value in these activities. That's the value-adding activity. This is what we call cycle time or value-creating time. If you've come across the DORA metrics from the State of DevOps report, we have lead time and these kinds of metrics. Lead time in DORA is essentially from this point, commit, to this point, deploy. But actually in Lean, it's not the right definition. Cycle time in Lean is the time a single activity takes, and then you sum it all up to get production lead time. You then have wait times in value streams, right? Which is the time that stuff is sitting around in a queue somewhere, building up in inventory, like in a car manufacturing plant, right? Sitting there doing nothing, right? Just existing without anything happening to it. So what this is saying is before the developers pick up a user story, on average, you get 2 days worth of stories sitting around. After they've finished development, sit around on average for 10 days, so 1 to 20 days. And then after it's been tested, sits around on average for 30 days. So this is like a 2-month release train, if you like, right? And then it gets deployed. So what this is showing us, I show you this is the wait time. This is the production lead times. The time it takes for a user story, a business idea, turned into a user story to go through this process, this very simple software development lifecycle, is 47 days, of which 42 of them, the work is sitting around doing nothing, not earning any money, not adding any value, just being a cost on our books. I mean, that's kind of bad, right? That's not great. 5 days versus 42 days of sitting around doing nothing. Not great. Of course, this has an economic cost, right? Because every day that something could be in production earning money is a day we've lost that money. So for those 42 days or 42 days of stuff sitting around, it's 42 days worth of stuff not making us money. If we could be earning 10 bananas for a feature going into production, a user story going into production, we've wasted lots of bananas. That's money we won't see. That's this kind of opportunity cost. Now, that's pretty simple value stream. Most value streams, probably in the organizations you work in, look a little bit more complicated. What we've ignored here is something that Donald Reinerson calls the fuzzy front end. So this is all the stuff that happens before work hits the development teams, right? And I've got an example, and also the other end, what happens afterwards. I've got a bit more of a realistic example from another client. So we created this using event storming, the technique from domain-driven design applied to path to production mapping. And what we can see in here is, again, this is a value stream where the blue cards represent value-adding activities. You're not supposed to read it, so don't squint, it's fine. So the blue items are work being done by people turning one thing into a more valuable thing. And it starts down here with a bunch of enterprise work. Actually starts down here with a business idea. This is the fuzzy front end. We've got a bunch of enterprise architects doing enterprise architect-y stuff. All really cool. We've got a bunch of solution architects doing solution architect-y stuff. And then we've got more solution architects doing more solution architect-y stuff because reasons. And then it hits this world of integration. This is an integration team that we were modeling. And these are interesting because these are two different data teams, each updating their canonical models. They just go round and round and round. They didn't know what canonical meant, I think, because it means one or sole source of truth. And then finally, some work pops out, and that blue card is a developer writing some code. That one. And then it goes into the testing phase, and we've got UAT, regression, performance, sit, handover, etc. Right? So 3 to 5 days a piece of work would sit in the development team on average. But the overall, actually we didn't even bother plotting the overall time because we showed this to the IT director and he went, what have we done to ourselves, essentially? But it's quite a long time. This is years worth of journey through this system of work. Now, there's other things on here that are interesting because they're the reasons work keeps sitting around in our teams, in our organizations. The first is coordination. We can see this here. I mentioned these two data teams. Coordination is when you're waiting for one or more other teams to do stuff before you can do a thing. Right? You must have come across this. I'm waiting for this team to finish an API before I can start using it. That sort of coordination. The data teams are causing that kind of wait for the development team because they're just cycling between each other. And until they're done, these folks can't get started. The next type of wait time is scheduling. You've probably come across this all the time. If you've got an architecture review board, a change request board, you have weekly or monthly meetings. This is cadence, this is scheduling, this is stuff waiting because you have to have a decision about whether it can proceed onwards, right? So architecture says no, committee says no, occasionally yes. So that's what we've got in here. We've got a 2 to 4 week wait for architecture review. So if you think about this, there's loads of work piling up in here, has to wait, stopped for 2 to 4 weeks for someone to go, yay, nay, and it could carry on flowing. And then all the work backs up for another 4 weeks and then flows through. Fun fact from Accelerate, I'm going to use this word precisely, change request boards, architecture review boards, predict low organizational performance. Predict is precise. If you have these things, it predicts your organization will be in the worst performing percentile of all the organizations they studied, right? The worst performing cohort. And you can kind of see why when I explain it like that. When you have these blockers on flow, it means everything has to stop, draining the system upstream and causing the system downstream to back up. It's a bit like when you get like a blockage in your arteries. You're putting back pressure up the system, pressure on the heart, if you like, causing the organization heart attacks, bizarrely. And the third form I'll talk about, queues and queuing. Now, queues and queuing, pernicious, right? We've got a Jira backlog. Cool, we've got a backlog. That's a queue. There's lots of other types of queues. So we've got queues of requested changes in the fuzzy front end. We've got queues of the changes that are waiting for solution options to be developed for them by the solution architects. We've got queues of work where the integration team is backed up, so they're waiting to pick that stuff up. And these queues can get big. Who's got a Jira backlog with more than 1,000 items on it? 1, 2. Who's not admitting it? 500? This is quite common, right? We get these massive backlogs where the stuff at the bottom is never going to get done, ever, right? Whether that's a really low priority bug fix, whether it's a manager who requested something that they've left, all these things back up in queues. And the problem with queues is the deeper the queue, the longer it takes for something to get from the bottom to the top. It's math, essentially. Daniel Terhorst-North, good friend of mine, he's got a lovely thing he does when he starts working with organizations. One of the first things he does is he looks at the Jira backlog, and if he thinks it's too big, he just deletes it all, and it will start again. No. We'll cleanse the system of Jira, if you like. And actually, sometimes we have all three of these things at once, right? Sometimes we have synchronization, coordination, and queuing. And that's why shared test environments should be nuked from orbit. Because shared test environments have all three of these problems associated with them. Often, right, you might have to schedule your use of a test environment at some point in the future. You might be queued up behind other people other teams who want to use that shared test environment. And you're often waiting on other teams to finish something because you need to test against their new version. You have all three of these conditions happening at the same time. This is one of the weird things about the economics of flow, is that you look at that and you go, oh yeah, that's probably bad, isn't it? All this stuff, if you've got 10 teams all waiting to use a very scarce resource, you've got 10 teams producing software that's not earning money. Usually, the argument against having more than one test environment is, oh, it's too expensive. We can't afford another SAP HANA license, right? We've only got one of them, or we can't afford, in the old days, another F5 or whatever it is, right? Because it costs 50 grand. Now, it's very quick. The time it takes to lose 50 grand's worth of value from 10 teams not being able to progress their software through the system is a really short period of time. It's bad economics. But unless you visualize the world of work, unless you understand the system in which you're working in, you won't really see those economic facts as they are, which is the stuff that's sitting around doing nothing isn't earning you money and should be, or should be saving lives, or whatever it is you do. So that's value streams. That's different types of wait time. Now I'm going to talk a little bit about things that we can do to improve flow through these systems. So I use an XKCD generator to do this, quite like this. And this is, I imagine this is like a CIO, and he's read some, I don't know, he's read CIO weekly or monthly or something. And he's gone, I just heard about this thing called a platform. We need a platform. It comes with the DevOps. Make me a platform. We'll go faster, right? And the dev says, yeah, sure, why not? Whatever, I need a DevOps, that'd be cool. The reason I'm talking about platforms is because platforms and platform thinking of a certain kind are probably the most effective way of improving flow in an organization. And it's because of queuing theory. Now, infrastructure as a service platforms in particular, and certain types of business platforms and development experience platforms operate as MMC queues where C tends to infinity. Now, I'm sure you all remember queuing theory from your networking 101 or whatever it was you did your queuing theory in. That's right, yeah, everyone's... No, shaking heads, right. I'll explain. I normally make a joke at this point and move on, pretending I'm not going to explain, but I don't want any of you to leave. so I'm actually going to explain. So it's a quick recap on queuing theory, or why we're often building platforms all wrong. And I hope this isn't too painful for some people who work in some of these environments. So what queuing theory does, we got a queue, it's a representation of a queue. We have producers, all right? If you're familiar with like RabbitMQ or any queuing systems, SQS, SNS, Kafka, it's all the same, right? You have producers pushing stuff into the queue. That's then normally denoted as lambda, and there's a rate of arrivals. Then you have a number of service nodes processing things off the queue, or if it's depending on whether you're doing competing consumer or not, different topologies, and then which are known as mu. And then you have the rate of departures. And of course, the rate of departures is dependent on the rate of arrivals, and it's dependent on the rate of speed of processing the arrivals off the queue and the number of these things you have, right? Now, the nomenclature refers to these things. So an MM1 queue is where you have these refer to the distributions of arrivals and departures, which we can ignore. An MM1 queue is when you have a single service node. So imagine you're queuing for, the supermarket, and there's a single till open. There's a bunch of people waiting to use that till. That is an MM1 queue, essentially. Or at an airport, waiting to check in, or any other situation like that. You then got an MMC queue, where C is the number of nodes you can add, right? And the number of nodes you add means that you can process items off the queue faster because you've got more of these things doing it. Pretty straightforward so far. So I said that that platforms were an MMC queue where C tends to infinity. And that's good, and I'll explain why. So traditional ops team is an MMC queue where C is the number of people you can hire, right? The number of smart, talented, awesome people working really, really hard in your operations team, processing tickets off ServiceNow, whatever it is, to create a new database or a new VM or whatever it is, right? You've got a bunch of people processing that stuff. The rate at which they can do it, the number of requests, and the depth of the queue is dependent on how many people you can hire. And they're expensive, right? Traditional ops team. Sorry for the swear. In ThoughtWorks, we've come to refer to this model as the half-assed or a broken private cloud, should we say? I don't know. This is where you take your ops teams and you put an API or WYSIWYG gateway in front of it and say, hey, we've got a private cloud, all right? Nothing else changes, right? You just got a nice point-and-clicky thing you can use, but you've still got the traditional ops team. So this is still an MMCQ where C is the number of people, but you're pretending it's not by putting a web interface on it. These two are functionally similar, except you've probably spent a lot of money, but I'm just building one of those. You can tell you've got one of these if beforehand it takes you 3 months to get a database, and then we've got a new private cloud, and afterwards it takes you 3 months to get a database, right? That's the signal that you're looking for. We've then got infrastructure as a service, and this is the crucial thing, and this is why I'm saying this is this is probably the best thing we can adopt to improve flow. Because infrastructure as a service, self-service infrastructure, completely flips this around. Because essentially, see, the number of people, number of nodes processing requests for stuff essentially becomes infinite, up to the limit of the hypervisor on the cloud you're using. Not instantaneous, you still have to wait for stuff to come up, but the number of requests becomes more or less infinite, which means self-service is super, super fast, right? It's the quickest way of getting stuff out of the way of your development teams. We've then got something else we keep seeing, which is like the worst of all possible worlds. It's where you've got this really, really cool infrastructure as a service doing self-service. Then you put something called a platform team on top of it to stop everyone using it. And now you've got to hire lots of really expensive platform engineers and put a nice GUI in front of them, right? So we're now again limited by the number of people we can hire. Infrastructure as a service, or platforms that provide self-service access to tools to build pipelines to observability, that kind of stuff. That's the best, probably, well, maybe best, maybe second best, joint best way of improving the rate at which we can get stuff done on our development teams, and therefore improving the rate at which we can deliver value and organizations can deliver value. Just to drive this home, you've got these 4 different types. 3 of them are expensive and slow. 1 of them isn't. And that is why AWS is a thing. Just to flash that because it's important. Which, yeah, if you want to know more about superficial private clouds, you can go to, my former colleague wrote a brilliant piece on Martin Fowler's site called What I Talk About When I Talk About Platforms. So this is the second part of that cartoon. Yeah, cool, we've got a DevOps and a platform. Okay, boss, we've implemented a DevOps. We have a platform too, but we still can't get anything done. And we see this in the wild all the time. You spend years, sometimes millions, and you still don't get any faster. And it's often because we mistake the fact that we're adding too many constraints over the thing that should make us go faster, which is self-service. Okay, quick sidebar. I'm going to this is another one of these curious things, which I hope you find interesting. Sidebar on generative science. So generative science is the use of simulations and models to simulate the real world, or to simulate aspects of the real world, so that we can ask questions of the models, and those questions, the answers in the model can tell us something about the real world. Now, I'll give you an example of this. This is birds flocking. If you've ever done Logo, the programming language, we used to use it to teach kids in school, right? So you have these turtles you move around. This is net logo, or multi-turtle logo, which is quite cool. So you can model these essentially. If you want to talk about agents and agentic systems, these are agents. This is an agentic system, right? I'm not even joking. This is true. That's a true statement, more or less. But what you can see in this, what you saw in that quick demo, was these little turtles or birds or whatever they are undergoing Brownian motion, random motion, right? Now, there's a set of parameters we can tune in this model. They include the distance the turtles, the birds can see, the rate at which they can turn, the speed, I think, that kind of thing. And you can fine-tune these, you can play with them. And the interesting thing about these simulations of something called complex adaptive systems, which is what this is that often these systems undergo a phase transition between one phase and another. And that's what happens here. So we slightly tweak the parameters. Very quickly, we see these agents undergo a phase transition towards something that looks like flocking behavior, right? And many scientists around the world who study complexity and other things in biology, in geography, in anthropology, use these models to test hypotheses, trying to understand what's going on. Here's a more concrete example that might be closer to home. This is another NetLogo simulation of viral spread in the population, right? So, and this is dependent on a number of factors, how close these agents get to one another. It's dependent on things like, the survival rate for the virus, et cetera, et cetera. And so we can use these to ask really interesting questions. I like genuinely, in some cases, life-saving questions. So I wasn't a participant in this, but ThoughtWorks were really privileged to actually participate in building this framework called EpiRust, which is an actor-based, to Brian in front row tip, agent-based model that at scale, right? So it's built in Rust, that can simulate millions, tens of millions of these agents. And we, as I say, that was then used to build something called Barrett Sim, and Barrett Sim was used during the COVID pandemic to do modeling for Mumbai. This is millions of people, right? So this is in the UK. I don't know if it happened here. In the UK, these models were the source of you wear a mask if you're in a room of more than 5 people, or you can't get within 2 meters of one another. That's where those rules came from, running these simulations. So you can get these interesting things. You can also prove, incidentally, that in any capitalist society, oligarchies are the norm unless you have strict market controls. You can also prove that trickle-down economics doesn't work. You can prove that under a steady state, if you have a set of agents, they've each got equal value at the start of stuff. They've all got 10 coins. At the end of the run, every time, there'll be one agent with all the coins and everyone else has got nothing. Sound familiar? Don't know. Yeah. But then the interesting thing is you can apply different market controls. They applied the market controls to the different countries in Europe in these simulations, and out pops something called the Gini coefficient, which is the ratio between rich and poor. Right. So you can actually get the accurate descriptions, statistical descriptions of the real world from these things. So back to following the work. Some more tips based on some of these ideas. So first of all, there's a book called The Principles of Product Development Flow. I want to pull some principles from that, because this is about the economics of improving flow in our organizations. The principle of congestion collapse. When loading becomes too high, we will see a sudden and catastrophic drop in output. So you're on your team, all right, you're all working away. I'm writing some code. The test has just tested my user story. Then some hippo turns up and says, stop everything. We need to work on this. It's the highest priority thing, right? And it preempts everything else that's going on in the queue. You're, oh, great, right, okay, well, we've got the test data loaded here. We've got all this basically it's a system that undergoes collapse, right? Suddenly you can identify these things because suddenly nothing's getting done. Everyone's working hard, doing stuff, but nothing's actually being produced at the other end. That's a system undergoing congestion collapse. I can demonstrate this with Logo as well, NetLogo. This is a very simple simulation of a highway. Obviously, in this, I'm not used to the roads in Bangalore, I have to admit. Bengaluru, sorry. And so this, I think, probably holds, but the speeds at which the cars move is different. What you can see here, if you have very simple set of parameters, when you run the simulation, there's no accidents, there's no other incident or anything, but you get this phase transition to bunching, right? These are cars traveling along a highway and they start bunching up. For no reason at all, apparently, right? No reason at all. And all that's controlling this is the number of cars, the rate of their maximum speed, the rate at which they can accelerate and decelerate. This is a system undergoing congestion collapse, right? The road is undergoing congestion collapse. But you can do stuff about this, right? We can learn what they do and things like highways and apply that in our own organization. So there's a principle called the peak throughput principle. Control occupancy to sustain high throughput in systems prone to congestion. So if I run this simulation again, everything else is the same apart from the number of cars in the simulation. You run the simulation again, and you come to this steady state. Doesn't undergo this phase transition to congestion collapse. And all you've done is remove the number of cars in the system on the road. Right? We do this actually in the UK. I'm not sure right here, but we do this in the UK by doing things like having traffic lights on ramps on the highways. So we basically limit the number of cars at rush hour who can get onto a highway. We can do this in our teams by adding work in progress limits on the different types of work we're doing, right? So if we have a work in progress limit on our development backlog, on our QA backlog, etc. These are real tools you can use. They're used in the real world. You can also do things like this, slow down. This is a bizarre thing. But if you slow down, you get the same effect. You can have more cars on a highway if they travel at a lower speed. This is why we have smart highways in the UK now. So depending on the throughput, depending on the amount of traffic, they'll drop the speed limit. This is why I'm saying I'm not sure if this translates, because I'm not sure how slow you'd have to go in Bangalore to get to this steady state. The next thing, the peak throughput principle. Control occupancy to sustain, so that was the last one. Control occupancy of a queue to sustain high throughput. So adding things like work in progress limits, and that will help you control flow. There's another interesting thing here as well, which is the principle of alignment, right? There's more value created with overall alignment than local excellence. What this principle is basically saying is if you've got 10 teams, it's better to have the 10 teams working at a constant rate than it is to have 9 of them blocked and one of them going really fast. All right, so optimize for the whole, not for the small. Now the second queue size control principle. Don't control cycle time, control queue size. I have a photo here, which is of me and Adrian Cockcroft, and that's Melvin Conway, who I mentioned at the start. Conway's Law, he's real, he exists. I just wanted to brag, I met him. Anyway, so the principle, that's better. Yeah, I'll move on from that. So I said this principle about controlling queue size and not cycle time. So the Dora metrics say, look at lead time for your teams, measure that, optimize that. Brilliant. The problem is that lead time is a trailing indicator of problems. Cycle time is a trailing indicator. You don't know you've got a problem when you're measuring lead time until after the problem occurs, right? Because then the lead time increases. Oh, wait, we got a problem, we're going to fix it. However, we can do something else. We can actually look at the amount of stuff sitting in a queue and use that as a leading indicator of problems. So here's a question in conferences I ask all the time. How long do you have to wait for lunch? Right? Normally conferences have very similar sets of lunchtime rules. You have a buffet, you have people queuing, you have a number of tables of the buffet, maybe a number of queues, but you have people queuing for lunch. So lunch is served at 1 p.m. You have a rate of arrivals of hungry people. So this is like all the people who weren't in sessions. They get arrived there. Then what happens is the session's finished, you get a thundering herd of hungry people, massive queues form, and then they are satisfied, leaving the queue. And this is the rate of departures from the queue. So the session's finished, some thundering herd arrives. Now, if you were to measure cycle time to try and understand whether you've got a problem in this system, you wouldn't know you've got a problem until way, way, way later. But if you measure the queue depth, if you just notice that there's a queue forming, you can address it immediately because it's a leading indicator. So you find out at 111 versus 135. This is what, again, supermarkets do, certainly in the UK, where, if there's a queue building up at the checkout, they'll actually have ding dong, and all people go to the checkout and help, and they'll open more checkouts or opening more counters at airports. That's because you can monitor the number of people waiting, and you don't have to then wait for the complaints afterwards. So the batch size queuing principle, reducing batch sizes reduces cycle time. This and self-service, and they're for similar reasons, this is probably the most important thing to think about when we're thinking about optimizing our systems for flow. So what do we mean by batch size in this case? So say you've got a set of requirements, right? You're building a product. This represents 2 products, version 1, and then the second version. So this is our MVP, then we've got another version going into production. In a stage-gated process, we talk about 100% batches. All the requirements have to be done, finished, have to be analyzed, developed, tested, integration tested, performance tested, regression, etc. It's not that surprising, right? Before they finally get deployed and start earning us money. So at that point, version 1 is deployed. At that point, version 2 is deployed. Version 1 is making us money. Version 2 is making us money. 2 big batches representing each of the versions. Just by splitting these up, just by reducing the batch size, the same amount of work, represents the same amount of work, the blue areas are the same. This starts earning money here. This starts earning money here. This starts earning money here. This here, this here, this here, this here. By the time we've got to this point, this has earned that much money, more money, because it would have been deployed here, right? Make sense? Yeah. This is why Agile is a thing. This is why continuous delivery is a thing. By breaking work up into thin slices and then deploying them when they're ready, right? We decrease the batch size and improve the rate of delivery of value. So batch size reduction, this is from Principles of Product Development Flow. Batch size reduction can enable us to shorten cycle time, often by an order of magnitude, without changing capacity or utilization. Now that should be a pretty extraordinary statement. That statement basically says you can improve your throughput to delivering value without adding more people, without having them work harder, just by doing work in these smaller chunks. But that's the hard bit, having really good analysts who can break stuff up into smaller chunks. Of course, we do that at ThoughtWorks really well. It's our secret sauce, actually, I would almost say. So I talked about how flow works. But I also had this thing about the curious domain model of how we work. I think I promised that. So talked about simulations, I've talked about flow, I've talked about the system in which we work. So I asked myself a little while ago, can we actually simulate this using generative science? Can we use the tools that we have to look at the real world and apply, simulate the real world and take some ideas from the simulations? So can we simulate the world of work? Well, if you think about this thing called complex adaptive systems, AI, agent-based models, maybe generative, maybe not, generative science and queuing theory, you smash these together and something quite fun happens. You get to be able to do this. If you remember my big value stream, this is the enterprise architect-y bit. I mentioned that all we do is we take stuff, do stuff to it, make it more valuable, turn it into other stuff. So we came up, me and my mates, with a bit of a domain model for how that looks. And this is what, we're all machines in my model. I apologize for that. It's better than resources, but not much. So you've got an enterprise architect machine. What they do is they take business requirements, documents, solution designs. They participate in the enterprise architecture, says no committee, and they produce solution options, right? They get, I've got the design I need to write, I'll do that thing, pass it on. Cool, I've got a different thing to do, I'll do that thing, pass it on. And these are participants in this value stream. These are the value-adding activities that the people involved in the value stream are performing on behalf of the artificial general intelligence we call the company. You can then model other stuff as well. You can model teams, physical machines, various other things using this model. You can model all these different types of wait time. You can look at things like queue preemption, reprioritization, all this kind of interesting stuff. You can then apply techniques from computer games and how NPCs, the AI for NPCs work. For example, this is a behavior tree. So behavior tree is a finite state machine as a graph, right? So, at the top you've got the overall goal, and then the leaves are the things you do to achieve the goal. There's other things you can apply as well, more sophisticated. And each of these enterprise architects has a set of behaviors that they follow, turning one thing into another thing, turning one thing into another thing. Then you can write all that up in some C#, which I did, and this is what it looks like in C#. You don't need to read that, but, handle, working on an item. I need to do some stuff. Cool, I'll do some stuff. And then you can write some software and visualize some stuff. And this is very early. This is a POC. I'm desperately trying to get funding for. Did I say that out loud? And what you can see here is two different types of team. One which is working as an agile team, single piece flow. Right? As one of the roles picks up a piece of work, they do it and pass it on. Developer, I pick up a story, write some code, commit it, pass it on. QA, there's a story ready for me to test. I'll run that, I'll move that back and run it again in a sec. The waterfall team, by contrast, a waterfall team using a stage-gated process, operating in 100% batches. Everything has to be developed before everything is tested, before everything is deployed. That's what these two different teams, this is what the simulation is between. And this is showing, you can see here, it's kind of like everything's blocked, waiting for everything else to be done. Agile team is delivering stuff, blocked. The end of the run, and the red line represents the value delivered by the agile team, blue line by the waterfall team. The red line represents the lead times of the agile team, blue line the waterfall team. Just by reducing batch size, just by operating in small batches, we've generated orders and orders of magnitude more value by working using the principles of product development flow. Can you wait to the end? Because I'm nearly done. Thank you. So I said at the start, artificial intelligence is already here. We call them companies, and we get paid to execute their algorithms very, very slowly. That's what I kind of want to mean. We're organisms participating in this chain of activities in a company, right? The company itself is formed of these sets of processes which grow and grow and grow over time. Interestingly, there's a lot of research that points to the fact that as the processes get longer, things get slower, and the company is more likely to die. Bizarre, true, but we participate in this cycle of doing stuff as knowledge workers, taking invisible work and turning it into more invisible, more valuable work. So how flow works, the curious domain model of how we work. Here's some tips based on those principles. The principles of congestion collapse. When loading becomes too high, we see a sudden and catastrophic drop in output. If you're on a team and suddenly stuff just isn't getting done, nothing seems to be flowing through it. Perhaps you're undergoing congestion collapse. Perhaps there's just too much work in the system, too much stuff happening. You've undergone that phase transition. The things you can do with that, or to help with that, is control occupancy. As an example, put work in progress limits in. We can only have 4 items under development at any one point. We're not going to have big queues of stuff ready or in development, right? Or in testing. Second queue size control principle, don't control cycle time, control queue size. If you put work in progress limits in, and you only allow 4 items in development at any one time, and if you have a ready for development queue that keeps growing and growing and growing and growing and growing, you know you've got a problem without waiting for the thing at the bottom of the queue to go into production at the end. Batch size queuing principle, reducing batch sizes reduces cycle time. Now, I said I've been on this journey. These are the books and the science that took me on this journey from 2017. Some canonical works here: continuous delivery, building microservices, building evolutionary architectures. I think this is like stuff we do that seems to work, right? This is about batch size reduction and about how we physically do that in our build pipelines. Building microservices, how we break things up in some parts into bits that can be worked on independently, the principle of modularity. Building evolutionary architectures, how we can do that and evolve systems safely. Principles of product development flow, the economics of the systems in which we work. Yeah. Often the economics are invisible, and only by visualizing these systems do those economics become visible. Accelerate, which is a great starting point to look at metrics for how we work. And team topologies about how our team structures can be optimized for flow. This is how it works. And my journey has been around complex adaptive systems and complexity science, and that's where the generative science part of this comes from, understanding how complex systems react and act together. There's a great book called Scale, which I've talked about a lot before, Quark and the Jaguar, by Murray Gell-Mann, he's a Nobel Prize winner who founded the Santa Fe Institute. This is about how you can build incredibly complex things like Jaguars from incredibly simple things like quarks. And then Complexity by M. Mitchell Waldrop, about its complexity science. I think it all flows from these principles. No, I did promise you a question, an answer, rather. You had the question. What would Lego Mega Bloks do in order to improve the experience of building big Lego sets for their client, for children, for adults building Lego? Anyone?
Hinted at it.
I hinted at it. Sorry? Smaller sets of Lego blocks. So you've got batch size. Any other answers? Group the pieces together. Hands up who's got kids who play with Lego. Yeah, all of those things are true. Oh yeah, I'm the big kids who play with Lego. In fact, all of those things are true. Lego underwent this interesting journey, right? So it started many years ago. You'd have these big boxes of Lego with just tons of bricks in bags, right? Tons of bricks in bags. But if you open a big box of Lego now, what you get is a bag with a 1 on it. And the number 1 bag is for the first 5 pages of the book. So you don't have to search around for stuff. You don't have to spend time doing that. They reduce the batch size. They also, interestingly, adopted the principle of modularity. So the principle of modularity is if you build stuff in parallel and then fit them together via a uniform interface afterwards, you get to go faster, right? Because you build stuff in parallel. This is at the heart, actually, of microservices. And they do that with the big Lego sets. If you get one of the really big ones, they'll have lots of different modules you can actually build separately if you've got loads of you. Then you plug them together via the uniform interface of this little pipe thing that clicks into place. So principles of modularity and reducing batch size. What would Lego do? That's what Lego would do. Yeah. Thank you very much. That's me for today. Thank you all for coming, and thanks for the welcome in Bengaluru.